In this video, we're going to review the concept of the electric field. Instead of calculating the electric force on two charges, we can look at just one charge and do this a little different way. This one charge, a positive charge, when any charge creates an electric field around it. If the charge is positive, then the electric field by convention points away from it, and if it's negative, it points toward it. So here you see positive charge, the electric field is pointing away. At all points it's pointing away from it. Here's a negative charge on the right, the electric field is pointing toward it. And basically the way the electric field is defined, if I put another charge in there, say a positive charge again, there will be a force on it, acting on it. The electric field is defined as how many newtons of force per coulomb of charge. This is how it's defined. So, at this point in space, right over here, say a distance r away from the charge, right at this point, there exists an electric field represented by a vector pointing away from that. The magnitude of the vector is given by this equation. Notice it's very similar to the Coulomb's law, except it's only one charge, one Q, and that's the charge of this charge at the center here. If I now place another charge at that point, right there, at the X, that charge will experience a force given by the equation on top. That force is equal to the charge I just put there multiplied by the electric field at that point. If the charge is negative, the force will be in the opposite direction. So let's do a sample calculation. Here we have a positive charge, say 12 microcoulombs. At the origin, what is the electric field at this point right here, which is 5 meters away from that charge? Again, the electric field is given by this equation here, where K equal to 9 times 10 to the 9th. So the electric field at that point will equal to 9 times 10 to the 9th, multiplied by the charge, which is 12 times 10 to the minus 6 coulombs, divided by the distance to this point, that's this distance, squared. So this will be 5 squared. And if you do the calculation, you will find that this comes out to be 4,320 newtons per coulomb. That means if we placed a 1 coulomb charge there, it would experience a force of 4,320 newtons. But we're going to put a different charge here. Let's say not 1 coulomb, but 6 microcoulombs. So if we place that at this point, this charge now will experience a force acting on it. The force is going to equal to QE. Let's make that charge an electron, so that we've just placed an electron on there. Therefore, the force on that particular electron, the force on the electron that I just put there, will be the charge of an electron multiplied by the electric field that we calculated, 4,320 newtons per coulomb. Of course, the charge of an electron is 1.6 times 10 to the minus 19 coulombs. So this will be the force acting on that charge. Now to get the acceleration is the force divided by the mass of the electron. So we're going to divide this by the mass of the electron, which is 9.1 times 10 to the minus 31 kilograms. And this comes out to be 7.6 times 10 to the 14th meters per second squared. So what we did is we placed the charge that we placed here, it was in fact an electron, and then therefore there was a force acting on it of E times 4320, and that enabled caused this electron to accelerate with that acceleration. Let's do a little more complex problem where we have two charges, and we want to calculate what is the electric field due to those two charges right here, the distance 3 away from the first charge and 2 away from the negative charge. Again, each charge contributes an electric field whose magnitude is given by this equation, and we have to calculate the direction of the field. So first of all, let's look at the negative charge, the yellow charge. It creates an electric field around it directed toward it, as you can see in these little arrows here. So at that point, there will be an electric field to the left, and of course the positive charge creates an electric field to the right. So the total electric field is going to be the sum, in this case the difference of those two vectors. So first of all, let's calculate the electric field due to the positive charge, the red charge, Q1. That'll be KQ1 over R squared, 9 times 10 to the 9th, multiplied by 12 times 10 to the minus 6th, divided by 3 squared. And that gives you 12,000 newtons per coulomb and it's to the right. Let's calculate the electric field due to the other charge, the negative charge or the yellow charge. It's going to be K, the magnitude of it will be KQ2 over R2 squared. Now R2 now is different because that distance right here is 2 meters. So it'll be 2 meters squared, 9 times 10 to the 9th, multiplied by minus 8 times 10 to the minus 6th, gives you a field of minus 18,000 newtons per coulomb. So the minus tells you that it's actually pointing that way. The total electric field at that point is the sum of those two, which equals 6,000 newtons per coulomb, and it's to the right. Now, if you have more than one charge and you're looking at the electric field away from the line connecting them, say at this point here, point over here, or for a matter of fact, anywhere along the bisector, you can see that the electric field is going to be to the right, in this case, if the charges are opposite. If the charges are the same and you look at that same line, you can see the electric field along the center here will be up. Anywhere along the center will be up. The further you get away, the smaller it gets. The closer you get, the bigger it gets. So let's do a calculation. Such a calculation, we have two opposite charges, and we're going to try to calculate the electric field right in the middle at this point right over here, what the electric field here is. So first of all, the positive charge creates an electric field that's away from it. The negative charge creates an electric field that's toward it. And so the net electric field is going to be the sum of those two, and we can see just by looking at it that the net electric field will in fact be in that direction, as we saw in the previous slide that it will be to the right. The calculations are done here. In order to add these two vectors, E1 and E2 as vectors, tip-to-tail method shows that they add up like this. To this vector E, we have to find the direction of E. We already know the direction, it's to the right, and we have to find the magnitude of E. And basically that involves finding the Y components, the X components, because the Y components cancel out. Each of these vectors that we originally had here has a Y component that cancels out the other one. So all we need to do, you can see the two Y vectors cancel out, so all we need to do is calculate the X component here in the bottom. It means the blue vector, and that component is equal to E1x is going to equal to E1 cosine theta, as shown in this equation, because cosine of this angle is equal to adjacent E1x over hypotenuse E1, and so E1, which will be the same as E2, is equal to E1 cosine theta, and the rest of the details here are over here. You replace the cosine of theta with adjacent over hypotenuse and do some simplification to get the final result.